The office is quiet this evening, but it won't quite sit still in my mind. The filing cabinet looks a touch too tall, the desk lamp a little too eager to sway, and every loose object, the mug, the paperweight, the stack of folders, feels like it's waiting for permission to move. I keep imagining the room as a fault in miniature, two stubborn surfaces pressed together, holding fast while an invisible push keeps building behind them. Nothing happens for ages. And then, all at once, the smallest slip changes everything. Papers skittering, blinds ticking against the window. The whole place reminding you that staying still can be an illusion. Good evening. If we haven't met yet, I'm Madeline Rowe, an astrophysicist turned private eye, trading telescope time for case files and calm explanations. Tonight's investigation is a steady one, filed under pressure and patience, under faults that hold for years and then let go in a second. So settle in close, let your shoulders unclench, let the room grow softer around the edges, and we'll open the Earthquakes folder together, slowly, carefully, one quiet page at a time. And apologies, I nearly forgot. If these calm case files help you unwind, you can subscribe so the next one is waiting for you when you're ready. All right then, let's begin. Let's begin the way any good investigation begins, not with the bang, with the backstory. For a long while, the Earth seemed to hold still. Mountains rose, oceans opened, continents drifted. But the common story, the polite story, was that the ground beneath our feet was permanent, a stage, not an actor. And then, quietly, the clues piled up. Not one clue, many. A shoreline that looks as if it could fit another shoreline. Rocks that match across an ocean as if they were torn from the same seam. Fossils, whole communities of ancient life, appearing on continents now separated by water too wide for them to cross. Strange scratches in stone, glacial marks pointing the wrong way, unless you accept that the continents once wore different coats in different places. In the early 20th century, the idea was spoken out loud, even if it wasn't welcomed. The continents might move. They might once have been joined. A single, sprawling arrangement of land that later fractured and wandered. The proposal was bold. The evidence was suggestive. And the world of geology at the time had a fair objection. Not to the pattern, to the engine. If continents drift, then what pushes them? How do you move something that big? How do you persuade rock to travel? It's easy, in hindsight, to imagine science as a simple march from wrong to right. But it doesn't move like that. It moves like a cautious committee. It demands mechanisms. It demands measurements. It demands that a beautiful idea survive contact with stubborn data. And for decades, plate motion stayed in the awkward middle, compelling in places, unconvincing in others, waiting for the kind of evidence that doesn't just hint, the kind that clicks into place. It arrived not as a single revelation, but as a chorus. Mid-century expeditions began to map the ocean floors in detail, really map them. The ridges running like seams across the basins, the deep trenches like long, narrow doubts. And then a signature no one expected to find so clearly, patterns in the magnetism of the seafloor laid down as basalt cooled, recording reversals of Earth's magnetic field like barcodes. Stripes that mirrored themselves on either side of mid-ocean ridges. Symmetrical, orderly, hard to dismiss. It was as if the planet was printing receipts, New ocean crust forms at ridges. It moves away. More forms behind it. And the old crust, the far-travelled crust, doesn't pile up forever. It disappears, drawn down into trenches, subducted, recycled into the mantle. Add to that the logic of transform faults, those sideways, shearing boundaries that connect segments of ridges and accommodate motion without creating or destroying crust. And suddenly, the story isn't continents drift like ships on water. It's plates move. A rigid outer shell broken into pieces, lithospheric plates, sliding over a warmer, weaker layer beneath. A theory that explains not one oddity, but many. Why mountain belts exist where they do. Why volcano chains arc and curve. Why ocean basins have their ages arranged like rings in a tree trunk. By the late 1960s, the pieces fit well enough that the scientific community had a framework that could do something precious. It could predict the kinds of features you'd expect to find. It could explain patterns that were already mapped, and it could tell you where to look next. That, in science, is a kind of acceptance you can trust, because it's earned. Now, once you accept plates move, you also accept something else. Their edges have to negotiate. They have to meet. They have to separate. They have to slide past. And when rock is forced to negotiate with rock, it doesn't do it politely. Not always. Sometimes it locks. Sometimes it loads. Sometimes, after long quiet effort, it slips. That slip is our case file. An earthquake is not the earth deciding to shake. It's not a mood. It's not a whim. It is the sudden release of energy stored in rock as stress accumulates and is then relieved by motion along a fault. A fault is simply a fracture in Earth's crust, or in the uppermost mantle, where blocks of rock can move relative to one another. And the important word is can. Because often they don't. Often they can't. Often the surfaces press together, rough and interlocked, resisting motion even while the plates keep trying. If you want a quiet image for that, imagine a heavy book on a wooden desk. You can push on it gently, nothing happens. You push a bit more, still nothing. The desk resists, friction holds, the book stays put. But the force you apply doesn't vanish. It accumulates as strain, tiny deformations, minute flexing. And then, at some point, the book jumps. Not because you changed your mind, because you reached the threshold where resistance could no longer hold. That's the essence, not perfect, but useful. In the earth, we call this stick-slip behavior. Stick, faults locked, stress building. Slip, sudden movement, energy released, waves radiating outward. There's a classic phrase too, elastic rebound. Rocks bend ever so slightly under stress. They store energy like a compressed spring. When the fault finally slips, that energy is released and the rocks rebound toward a less strained state. The motion is usually measured in centimeters to meters, depending on the event. The slip itself may occur over seconds to minutes, but the loading can take years, decades, centuries. That's part of what makes earthquakes feel so personal, so unfair. The preparation is slow and silent. The release is fast. And as the fault slips, it doesn't slide like a door on oiled hinges. A rupture front propagates along the fault, like a tear racing through fabric, activating one patch after another. Some parts slip more than others, some stop, then restart. Faults are not perfect planes. They are complex surfaces with bends and branches and zones of crushed rock. So the earthquake, the event we talk about as if it's one thing, often contains a whole choreography of motion inside it. Now, let's widen the view, because the Earth doesn't distribute earthquakes evenly. If this were purely random, our maps would be speckled. Instead, they are traced. Lines, arcs, belts, the outlines of plate boundaries. The places where plates diverge, converge, or slide past. At divergent boundaries, mid-ocean ridges, the plates pull apart. Hot mantle rises, melts as pressure drops, a new crust forms. Earthquakes happen there, but they are typically shallow. The crust is thin, hot, and comparatively weak. The faults don't usually store the colossal stresses needed for the very largest events. So you get frequent, smaller quakes, one kind of signature of a boundary that's always making something new. At transform boundaries, plates slide past each other. Think of the San Andreas Fault as a famous example on land, though transforms also stitch the mid-ocean ridges together in the deep. Here, earthquakes can be shallow and sharp. The motion is mostly sideways, strike-slip. And because the plates are trying to move steadily, but the fault locks in places, the stress can accumulate until it breaks free in sudden steps. Transform faults can produce large, damaging earthquakes, particularly where people have built cities across the seams. At convergent boundaries, plates collide. And here, we need to slow down, because convergent boundaries come in flavors. If two continents collide, neither wants to subduct easily. Continental crust is buoyant, so the crust shortens and thickens. Mountain belts rise, earthquakes occur as rocks fold, and fault, often on thrust faults, where one block is pushed up over another. If an oceanic plate meets a continental plate, the oceanic plate is generally denser and sinks. It subducts beneath the continent. If an oceanic plate meets another oceanic plate, one subducts beneath the other, and you get an island arc. Subduction zones are special, not just because of volcanoes and trenches, because subduction zones host the largest earthquakes the planet can produce. The giant, sprawling ruptures on megathrust faults, those boundary surfaces where one plate dives beneath another. These are the events that can move huge slabs of the seafloor and, in doing so, displace the ocean itself. Which is how earthquakes can become tsunamis. Not because the quake is big, because the motion is the right kind of motion in the right place. Subduction zones also give us a vertical map. Earthquakes there don't just trace a line at the surface. They form a dipping plane of seismicity that descends into the earth along the subducting slab, from shallow quakes near the trench down to intermediate and deep earthquakes hundreds of kilometers below. That depth range tells us something important. It tells us that the subducting plate remains a coherent, cold slab for a long time as it sinks. And it tells us that earthquake is not one mechanism everywhere. Shallow earthquakes are dominated by brittle failure, fracturing. Deep earthquakes happen under pressures where rock shouldn't fracture the way it does at the surface, so the mechanisms are more subtle. Still an active area of research, with competing explanations involving mineral changes and localized weakening. But for our purposes tonight, the main point is calmer and simpler. Earthquakes are how the Earth spends the stress generated by plate motion. They are one of the ways the planet balances its books. Now, because we're being thorough, we should mention intraplate earthquakes. Quakes that happen away from plate boundaries. They're less common, but not non-existent. The interiors of plates still feel stress, transmitted through the lithosphere, influenced by boundary forces, by mantle flow, by old scars in the crust. Ancient faults can be reactivated. Old rifts can awaken. The Earth has a long memory in its rocks. So while plate boundaries are the main avenues, the interior is not immune. It's simply quieter. Now, before we move on, I want you to notice something about the way we've been talking. We've been describing where earthquakes happen and why, but we haven't said how we know. How we take a sudden event, often happening offshore or deep underground, and reconstruct its shape. This is where the detective tools come out, with another kind of listening, not to waves, to slow motion. Because even when a fault is quiet, the plates are still trying. They're always trying. So one of the cleanest ways we study earthquakes is by measuring what happens in the years between them, when nothing dramatic is happening at all. We do it with geodesy, measuring Earth's shape and motion with absurd patience. With GPS stations bolted into bedrock, returning a steady stream of positions day after day, millimetre by millimetre. With radar satellites that pass overhead and compare the phase of the signal on different dates so we can map tiny changes in the ground. Patterns you would never see with your eyes, but that a careful instrument can trace like fingerprints. Over time, those measurements draw a map of strain, a quiet tug of war. In some regions, the ground moves smoothly. A fault creeps, sliding slowly, continuously, relieving stress without a single sharp release. In other places, the measurements show the opposite. The surface looks almost stuck, even though the plates are still pushing. That stuckness is information. It's the signature of a locked fault, storing elastic strain. And sometimes the map shows something in between. A slow slip event, motion that happens over days to months, too gentle to radiate the high-frequency shaking we associate with an earthquake, but real movement nonetheless. Like a door that doesn't slam but eases open in the night. Slow slip doesn't replace earthquakes, and it doesn't guarantee them. But it does tell us something important about how faults behave. That faults are not simply on or off. They are surfaces that can slide in different modes, depending on pressure, temperature, fluids, and the roughness of the interface. It's one of the reasons prediction is so hard, because the same boundary can behave like a spring in one segment, like a zipper in another, and like a slow, quiet conveyor belt somewhere else. Still, this slow motion evidence is precious. It anchors the story. It reminds us that earthquakes aren't random lightning strikes. They are part of a continuous mechanical process, a steady loading punctuated by sudden release. And once you've seen the planet move millimeters at a time, recorded patiently for years, it becomes easier to understand why a few seconds of rupture can carry so much stored work with it. Now, with that long, slow motion in mind, we can go back to the faster language of earthquakes, the waves they send, the way we catch them, and the way we measure what just happened. Seismology is at heart the art of listening to the earth. A seismometer is an instrument designed to record ground motion. If the ground moves, the instrument senses it and draws it as a function of time. A seismogram. A quiet scribble that can, with practice, tell you an entire story. When an earthquake ruptures, it sends out waves, different kinds of waves, travelling at different speeds, moving matter in different ways. P waves, primary waves, are compressional. They squeeze and stretch the material in the same direction the wave travels. They are usually the fastest seismic waves, which is why they arrive first. S waves, secondary waves, are shear waves. They move the ground side to side or up and down perpendicular to the direction the wave travels. They are slower than P waves and do not travel through liquids. Then come the surface waves, which travel along Earth's surface and often do much of the damage far from the source. They can roll, they can sway, and because they're trapped near the surface, their energy can persist. If you've ever seen footage of tall buildings gently oscillating long after the initial jolt, you're watching the conversation between surface waves and structure. Now, if you record an earthquake at a seismometer, you get arrivals. A first wiggle, often the P wave. Then, later, another arrival, the S wave. Then the surface waves. The time gap between P and S arrivals depends on how far the quake is from the station. Bigger gap, farther quake. So if you have multiple stations, you can use those time differences to estimate distance, then triangulate location. Not perfectly, not instantly, but reliably. With a global network, you can locate earthquakes anywhere on the planet. And you can go further, you can estimate depth, you can estimate the size. You can even infer the style of faulting, whether the quake was mainly strike-slip, normal, or reverse, by looking at how the waves radiate, where they compress, where they dilate. The quake leaves a fingerprint in the wave field. Now, about size. People often talk about earthquakes as if they come with one number, but size isn't just one idea. There's the energy released, there's the amplitude of waves at certain frequencies, there's the area of the fault that slipped, there's the amount of slip, there's the shaking experienced at the surface, which depends not only on the quake, but on distance and local ground conditions, and building design, so seismology uses different measures for different questions. Magnitude is a measure of the earthquake's source size. Modern seismology often uses moment magnitude, based on seismic moment, which is tied to the fault area that slipped, the average slip, and the stiffness of the rocks involved. It's designed to behave well for very large earthquakes, where older magnitude scales saturate. Intensity is different. Intensity describes how strong the shaking felt, or how much damage occurred at a particular location. One earthquake can produce different intensities across a region, because the shaking varies with distance, geology, and the built environment. This distinction is important for calm thinking. Magnitude is about the earthquake itself. Intensity is about what the earthquake does to a place. Now let's take a slow walk through a familiar scenario. A quake occurs offshore along a subduction zone. The fault ruptures. Some part of the seafloor is lifted and dropped. The waves radiate outward through the earth, and around the earth, and along the surface. A station on the coast records P waves, then S waves, then surface waves. Farther away, another station records the same pattern, delayed. Across the ocean, stations on another continent record it again, delayed more. From these arrivals, scientists estimate the quake's origin time, location, depth, and magnitude. Within minutes, you can have a first solution. Within hours, you can refine it. Within days, you can build a detailed model of the rupture, how slip varied, where it concentrated, how the rupture propagated. It's one of the quieter achievements of modern Earth science. We can't see the fault deep below, but we can infer it from the waves it sends. Now, if you're listening to fall asleep, you might be thinking, politely, Madeline, this is all very neat, but where is the part where the Earth shakes? We're arriving, because the next question is what happens after. And this is where earthquakes stop being isolated events and start behaving like sequences. Aftershocks are earthquakes that occur after a larger earthquake in the same general region. They are not the Earth echoing. They are the fault system adjusting. When a main shock happens, it changes the stress field around it. Some patches are relieved, others are loaded, A large earthquake can bring nearby faults closer to failure or move them farther away. And because the crust is complex, faults interacting, fluids moving, rock properties varying, the post-main shock period can contain many events. Aftershocks typically decay in frequency with time. Many sequences show a pattern where the rate of aftershocks drops roughly as a function of time since the main shock. Fast at first, then gradually quieting. But not instantly, and not uniformly. Some sequences linger. Some areas remain active for months or years. Now, foreshocks. Foreshocks are earthquakes that happen before a larger earthquake in the same region. The tricky part is that you cannot know an earthquake is a foreshock until after the larger event occurs. Beforehand, it looks like any other earthquake. And most earthquakes are not followed by a larger one nearby. So foreshocks are real, but they are not reliable warnings in the way people wish they were. This matters because there is a human hunger for certainty, for omens, for a sign that tomorrow will be rough. The honest scientific posture is calmer and less satisfying. Earthquake sequences have patterns, they have statistics, they have probabilities. They do not have dependable universal precursors that allow you to say with confidence, time and place and magnitude. Not yet, and perhaps not ever in the way people imagine. That brings us to one of the most important distinctions in this file. Prediction, forecasting, early warning. Prediction, in the strict sense, means you specify the time, location, and magnitude of an earthquake in advance with enough accuracy to be useful. Forecasting is probabilistic. It says something like, in this region, over this time window, the chance of an earthquake above a certain size is this. Early warning is different again. Early warning happens after an earthquake has already begun. It uses the fact that P waves travel faster than the most damaging waves, and that electronic communication travels faster than seismic waves. So if you can detect the quake near its source quickly, you can send an alert to locations that will feel strong, shaking a few seconds later. Not minutes, seconds. Sometimes a handful, sometimes more, depending on distance. And those seconds can matter. They can allow trains to slow, elevators to stop at the nearest floor, gas valves to shut, surgeons to pause, people to take cover. It doesn't stop the quake, it doesn't predict the quake, it reacts quickly to the quake that has already started in order to reduce harm. This difference is worth repeating gently because it keeps the science clean. Forecasting is about long-term probability. Early warning is about rapid response. Prediction, as popularly imagined, remains elusive, and the best use of scientific effort in many regions is not to promise certainty, it is to reduce vulnerability. Because forecasting is about probabilities, the next question is always the same. How do we know what a fault has done before? Not just in the last 100 years, not just since we've had instruments, but in the deeper past, where the Earth has been keeping records in its own handwriting. This is where the case file becomes geological, because faults leave evidence, not always obvious evidence and not always tidy, but enough if you look in the right places, with the right patience. A fault that reaches the surface can offset layers of sediment. A river terrace can be cut and shifted. A soil horizon can be broken and overlain by a newer layer, as if the ground itself turned a page. So in some regions, scientists dig trenches across active faults, long, careful cuts into the shallow subsurface, so they can read the layers like a timeline. They look for disrupted strata, for tiny colluvial wedges where a scarp collapsed and was later buried, for repeated breaks that suggest repeated events. And then comes the slow work of dating, not to make it dramatic, just to bound the story, to say, This earthquake happened after this layer formed, and before that one did, to build a sequence of past ruptures spaced over centuries or millennia. This is paleoseismology, earthquake history written in sediments. It's one of the reasons we can talk about recurrence intervals at all, not as schedules, not as promises, but as rough patterns. Some faults produce large ruptures every few hundred years, give or take. Some slip more frequently in smaller events. Some show clusters, busy periods separated by long, quiet gaps. And even when the record is incomplete, it's better than guessing. Because a fault without an instrumental history is not a fault without a history. It's simply a fault we haven't read properly yet. This kind of evidence feeds into hazard models. It helps estimate how much slip a fault accommodates over time, how big a rupture could reasonably get, and how often the system tends to release strain in large events. From there, scientists and engineers build maps, probabilistic seismic hazard maps, that don't say an earthquake will happen here on this date, but instead describe the likelihood of certain levels of shaking over certain time windows. And if that sounds abstract, it becomes practical very quickly, because those maps inform building codes, they inform retrofits, they inform where critical infrastructure should be strengthened and how. In other words, they turn deep time geology into present tense safety. Not through certainty, through preparation. And once you've watched the Earth's past earthquakes revealed in a trench wall, quiet layers, interrupted by sudden breaks, you begin to see mitigation as the most grounded form of earthquake science. Not the loud part, the useful part. The part that keeps the next chapter from becoming a catastrophe. Now, vulnerability comes from more than the shaking itself. Earthquakes have secondary hazards, effects that are triggered by the shaking. Liquefaction is one. If you have loose, water-saturated sediments, often in river deltas, reclaimed land, coastal plains, the shaking can cause the grains to lose contact and the material to behave temporarily like a fluid. The ground can settle, it can spread laterally, structures can tilt, pipelines can break. It's not that the soil turns to water, it's that the effective strength drops because pore water pressure rises and the grains stop carrying load the way they usually do. Landslides are another. Shaking can destabilize slopes, especially those already close to failure due to rainfall, geology, or human modification. Rockfalls can be triggered in steep terrain. Whole hillsides can move. And if a landslide enters a body of water, lake or fjord or reservoir, it can generate waves of its own. Tsunamis, of course, are among the most far-reaching secondary hazards. A tsunami is not a tidal wave. It's a series of long wavelength ocean waves generated by displacement of water, often due to seafloor motion in a subduction zone earthquake, but sometimes due to landslides or volcanic collapses. In the deep ocean, tsunamis can travel fast with low wave height, almost unnoticed by ships. Near the coast, as the water shallows, the wave slows and grows in height, compressing its energy into a rising wall or a rapid surge. The danger is not only the height, it's the volume of water moving with force, arriving in multiple waves, sometimes with the sea drawing back first, exposing the seafloor in an eerie preview. This is why coastal tsunami education emphasizes unusual sea behavior after strong or long shaking. Now, there's another secondary hazard that doesn't get the same poetic attention, but does real harm: fire. If infrastructure is damaged, gas lines, electrical lines, fires can start. And if roads are cracked or water systems are broken, firefighting becomes harder. Earthquake risk, in practice, is often a compound risk, not a single blow, but a cascade. Which is why mitigation matters. Mitigation is the part of this story that feels most human. Not because it's sentimental, because it's where choices make measurable differences. Building codes, retrofitting, land use planning, securing heavy furniture, designing bridges and lifelines for shaking, training people in simple protective actions during shaking, drop, cover, and hold on. It's not glamorous, but it's effective. In many places, the most important earthquake science is not the science that tries to foresee the exact moment of rupture. It's the science that maps hazards, informs engineering, and reduces the damage when the inevitable happens. Now, let's drift back to the plates for a moment. Because the quiet truth is that plate tectonics is not only a story of the present, it has a history in deep time. The Earth has cooled over billions of years. And as it cools, the properties of its lithosphere, the strength, the thickness, the buoyancy, change. Some researchers argue that plate tectonics, in some form, began early, while others debate when it became global and sustained. A useful way to hold this gently is this. Earth's style of tectonics likely evolved. Early Earth was hotter. Hotter lithosphere behaves differently. Subduction may have been shallower and more short-lived in very early times, transitioning towards the colder, steeper, deeper subduction we recognize today. Even in the modern era, the system is not a static machine, it's a dynamic regime. And that takes us naturally to another long time scale pattern, the supercontinent cycle. Over geological time, continents have assembled into large combined land masses, then broken apart, then assembled again. The cycle is measured in hundreds of millions of years, slow enough to be invisible in a human lifetime, but real enough that the rocks remember it. There's a quiet question buried in that cycle. When continents assemble into the next supercontinent, which ocean closes? Sometimes the internal oceans formed during breakup close again, a style sometimes called introversion. Sometimes the external superocean around the old supercontinent closes instead, a style called extraversion. And there are ideas in between too about preferred directions of assembly tied to mantle structure. The key point for tonight is that scientists can use models, geodynamic models, to explore what conditions favour one assembly path over another. One line of work suggests that the strength of the oceanic lithosphere plays a critical role. In their modelling, stronger oceanic lithosphere can favour one kind of assembly, while weaker lithosphere favours another. And because Earth has cooled over time, the thickness and strength of oceanic crust may have changed in a way that shifts the dominant assembly mode across geological eras. This is not fortune-telling. It's not a prophecy. It's a hypothesis generated by physics-based modelling under specific assumptions. And it comes with debate, as good science does. But it offers a calm, slow thought. Earth's future geography is constrained not only by where the plates are now, but by how the system's properties evolve as the planet continues to cool. Within that framework, some researchers propose that the next supercontinent, sometimes named Amasia, may assemble through closure of the Pacific Ocean, rather than closure of the Indian and Atlantic. The Pacific is already rimmed by subduction zones. It already spends old oceanic crust by pulling it down. So it is, in a sense, already in the act of closing, even if the timescale is long beyond our lives. Now let's bring this down from deep time to the immediate, the local, the tactile. Because if you live on Earth, you live on a moving planet. Even if you never feel a quake, Even if you never see a fault, plate motion is slow but relentless, centimeters per year, the speed your fingernails grow. And yet, accumulated over decades, it is enough to load faults, to store energy in rock, to keep the case file active. So how do we live with it? We start with the simplest, most honest map. Hazard is not the same as risk. Hazard is the likelihood of strong shaking. Risk includes exposure and vulnerability. How many people, how many structures, how well they are built, how prepared they are, how resilient the infrastructure is. You can't choose whether the Earth has plate tectonics, but societies can choose how brittle they are in the face of shaking. That choice is made in architecture, in policy, in education, in maintenance, in whether older buildings are strengthened, in whether bridges have retrofits, in whether hospitals and emergency centres are designed for the shaking they are likely to experience. Now, since we're being calm and practical, let's paint a gentle picture of what early warning looks like, because it's often misunderstood. Imagine a quake begins on a fault. Near the source, P waves radiate outward. A nearby station detects them within seconds. A computer identifies the pattern. It estimates the location and magnitude, initially rough, improving as more data arrive. An alert is sent electronically. Farther away, the stronger S waves and surface waves are still travelling through the Earth. The alert can arrive before the strong shaking does, not by predicting the future, by outrunning the waves. Early warning is a race. Sometimes you win by a few seconds. Sometimes you don't win at all if you're too close to the source. Sometimes the first magnitude estimate is off and is revised. The system is not magic, but in many cases it buys time. And time, in emergencies, is worth a great deal. Forecasting is slower, quieter, and less cinematic. It uses historical seismicity, fault slip rates, geologic evidence of past earthquakes, and statistical models to estimate probabilities. It can't say Tuesday at 3:12, but it can say this fault system is capable of a large event, and over the coming decades, the probability is significant. That's the kind of statement that justifies building codes, retrofits, and planning. It's the kind of statement that, if taken seriously, saves lives. Now, because this is a case file and not a bedtime fairy tale, we should address the temptation to treat every small oddity as a warning. Unusual animal behaviour, strange lights, a feeling in the air. In the history of earthquakes, people have always looked for omens, and sometimes, by chance, an omen will precede an event. But chance is not a mechanism. The hard scientific problem is that earthquakes are rare in any specific location on human timescales, and the Earth is noisy. Many odd things happen all the time, and most of them do not lead to earthquakes. Without a reliable, repeatable signal that can be demonstrated to predict beyond chance, omens remain stories rather than tools. That doesn't mean scientists don't study possible precursors. They do. They look at small quakes, slow slip, geodetic deformation, fluids, changes in seismic velocity, and more. But the honest state of the field is restrained. No universally reliable method exists to predict the exact time and place of large earthquakes with the certainty people crave. So the best posture is a quiet one. Prepare, mitigate, educate. Listen to hazards, not rumours. Now, let's take a slow tour, almost like a stroll at night, through the three main plate edge styles, because each has a characteristic feel in the earthquake record. At a spreading centre, the crust is born hot. Faults are young, small, and shallow. Earthquakes there are frequent, but usually moderate. They're part of the steady cracking of new crust as it cools and stretches. It's the Earth's way of accommodating extension. At a transform boundary, the fault is often long and continuous. The motion is lateral. A transform fault can store stress along locked patches, then release it in sharp, sudden ruptures. These quakes can be shallow and intense because they occur close to the surface. In populated regions, shallow shaking can be particularly damaging because there is little distance for waves to attenuate before they reach buildings. At a convergent boundary, especially a subduction zone, the story is larger. The fault surface can be enormous, hundreds of kilometers long, tens to hundreds of kilometers wide. The plates can lock for decades or centuries, accumulating immense strain. Then, when the megathrust ruptures, the slip can be meters. The seafloor can move, and the consequences can extend far beyond the region of strong shaking, out across the ocean in the form of a tsunami. These are the events that remind us that Earth's tectonic engine is not merely local, it is planetary. Now, if you're still awake, let's slow it down further with a quiet thought about ground itself. Because even if the earthquake source is the same, the shaking you experience can vary dramatically depending on what you're standing on. Hard bedrock transmits seismic waves differently than soft sediments. Basins can trap and amplify certain wave frequencies. Loose soils can resonate. This is one reason why two neighborhoods in the same city can experience different shaking intensities. It's why seismic hazard maps don't just show faults, they show geology. And it's why a careful engineer is always asking not only how big is the earthquake, but what is the ground beneath the structure. Buildings, too, have their own behaviour. Every structure has natural frequencies, ways it prefers to vibrate. If the dominant shaking frequency matches a building's resonance, the oscillations can grow. This is why building design matters, and why some structures fail while others sway and survive. Good seismic design is not about making a building rigid. Often it's about allowing controlled motion and dissipating energy through ductile materials, through base isolation, through well-detailed connections, so the structure can absorb shaking without catastrophic collapse. Again, not glamorous, but measurable. Now, let's return to sequences, because one of the most common questions people ask after an earthquake is it over? The honest answer is, the main shock is over, but the sequence may continue. Aftershocks can happen, sometimes large enough to cause additional damage to already weakened structures. This is one reason why post-earthquake safety guidance emphasizes caution around damaged buildings, and why inspections matter. The Earth does not always stop moving just because the biggest movement has happened. It settles, and it settles on its own schedule. Now, because we're building a mental model that you can fall asleep inside, let's stitch this all together into one calm picture. The planet's outer shell is broken into plates. The plates move slowly, driven by the planet's internal heat and the dynamics of mantle convection and gravity. Where plates interact, the crust deforms, sometimes smoothly, sometimes in bursts. Faults are the surfaces along which rock blocks can slip. Many faults are locked much of the time. Stress accumulates, strain builds. When the fault strength is exceeded, rupture occurs. Energy is released. Seismic waves radiate. We record those waves. We locate the event. We estimate its size. We map patterns. We model hazards. We design structures. We teach people simple protective actions. We accept that we cannot schedule earthquakes on a calendar. but we can reduce the damage they do. And all of it, every shaking event, fits into the larger story of plate tectonics, a story that itself has a history. An idea proposed, resisted, strengthened, formalized. A story supported by seafloor patterns and deep earth structure. A story still evolving as scientists model how the system has changed through deep time. Now, because we began with history, it feels right to end with time. Not the time on a clock, the time in rocks, the time in oceans opening and closing, the time in continents assembling and dispersing. If you zoom far enough out, Earth's tectonics is a kind of breathing. Not fast, not rhythmic in any simple way, but cyclical on the scale of hundreds of millions of years. Oceans open, oceans close, mountains rise, mountains erode. And through it all, earthquakes are the small, sharp syllables in a long sentence. The clicking of stress being released. The quiet accounting of motion. Somewhere out there, on the far edge of human imagination, plates will continue to rearrange the map. The Pacific may narrow. The continents may converge into a future supercontinent. The details are uncertain. The models have assumptions. The debates continue. But the direction of the thought is steady. Earth is not finished. It is not a completed sculpture. It is an active system, and your life, tonight, in this room, is happening on the surface of that system, like a warm light in a very old machine. So if you're ready, let's do what we do at the end of a case file. A slow recap. Earthquakes are the sudden release of energy stored in rock as stress accumulates and is relieved by slip on a fault. Most earthquakes occur along plate boundaries, where plates diverge, converge, or slide past. Subduction zones can produce the largest earthquakes and, when the seafloor is displaced, tsunamis. Seismic waves, P waves, S waves, and surface waves carry information about the event and allow us to locate it and measure it. Magnitude describes the source size of the earthquake. Intensity describes the shaking effects at a location. Aftershocks are common as the crust adjusts to stress changes after a main shock. Exact prediction remains elusive, but probabilistic forecasting and rapid early warning are real tools, each useful in its own way. And the most reliable way to reduce harm is mitigation. Sound building practices, retrofits, preparedness, and clear safety guidance. If your eyes are already heavy, you don't need to hold on to every detail. Let the ideas drift. Let them become background, like rain. Just remember the simplest, calmest picture: a moving planet, a patient planet, a planet that stores stress and releases it, not out of anger, but out of physics. And if you ever need the practical advice when you're awake, during shaking, drop, cover, and hold on. Stay away from windows and tall furniture, and follow local emergency guidance for your region. For now, though, there's nothing you need to do. The office is quiet. The file is closed. The lamp can dim, and you can let the whole earth go back to being what it usually is in the mind at rest. A steady place to sleep. Good night.